Assalamualaikum and good morning to our lecturer, Dr. Nurkali David Zakaria. Today we are going to present our project, which is Electric Vehicle Monitoring System. We are from Group A. My name is Nazrul Hakim bin Anwar, and these are my team members, Muhammad Azim bin Muhammad Zaman and Azri Syafiq bin Ahmad Suhaimi. To begin our presentation, we will look at the main issue that inspired this project. Moving on to our problem statement, for this project, we are focusing on a critical safety issue regarding electric vehicles. As you can see from our flow, this problem begins with the trigger. In Malaysia, we constantly face extreme heat. When this high temperature is combined with continuous high-speed driving, it puts massive stress on the EV's component. This directly leads to severe safety hazard. This vehicle is at a very high risk of experiencing sudden tire blowout and battery thermal runaway. To prove this, we have included real news clipping here, include report from the fire department showing that spontaneous EV fire are real and life-threatening danger on our highways. So why do this accident keep happening? It is because of the current system gap. Standard EVs lack the ability to detect this multi-variable abnormal condition early. So, drivers are completely unaware of the rising heat and pressure, and by the time a warning appears, it is usually too late. So, this critical safety gap is exactly why we developed our project. Now, let's focus on flowchart. It begins with the start terminator. The script uses G down to download the EV dataset and convert the raw CSV file into a data frame array. To simulate real-world driving condition, the script loops through each row, and for every row, it packages a JSON payload with 5 vehicle parameters. To run a mandatory 10-second time delay using timesleep 10 to match hardware sampling rates, and also transmit the data via an HTTP post request to the ThinkSpot telemetry API endpoint, and then it passing control to a point A. Now, at connector A, the data enters the parallel processing and dual condition alarm validation phase. Inside the rule engine, to eliminate processing lag, the engine checks these 5 exact safety thresholds simultaneously, which is battery temperature, if it's exceed 50 degrees Celsius, and battery voltage, if it drop below than safe 250 volt, while tire pressure checks if thermal buildup exceeds 50 degrees Celsius, and tire pressure evaluates inflation breaches 33 psi, and lastly, driving speed monitored against safety limits at 100 km per hour. Each path maps to a strict dual condition logic path. If a threshold is violated, yes branch, a trigger alarm sets active warning 1. If parameters are safe or recover, no branch, a cleared alarm reset active status into 0. This ensures active flags clear themselves automatically in real time. Control then drops the connector B. Finally, from connector B, we enter data consolidation, visualization, and life cycle termination. All parallel branches converge, and then the system executes a backend command to save the data point and the active status flags permanently to the device history registry database. Simultaneously, it updates the cloud host web UI dashboard, refreshing the digital gauge meter, updating historical tracking charts, and adjusting the global warning panel counters. The terminal diamond tests for data exhaustion are the more row remaining in the CSV. If the CSV file has more, then it's conclude to yes. Then the logic flows through the connector C right back to the loop entry point to process the next row. Then if no, the loop at break. Execution safely stop at the end terminator, and the monitoring session complete shutdown.
Moving up, this is the main code to transfer the data from our Jupyter notebook to the dashboard. So we're going to the first important coding. first we need to specify the location of dataset so the program know exactly where to fetch it. In this case, our dataset are located in the drive, so we include the drive link into our coding. And then the next line is download dataset from Google Drive to Jupyter. So we need to instruct the code to download the dataset into our workspace so we can use it for our next step. And then the next line is read file downloaded. So we need to read the file and preview it to make sure the data we downloaded is correct. And then next we need to set up the ThingsBot API. So this setup will be act as the destination where we will send our data. And then finally we send the data row by row to the ThingsBot, and we also include the time delay between each row to simulate the real-time data. Now let's look at the dashboard. So once we run the code, the data will appear immediately in here. So this dashboard is divided into 4 main sections to monitor the EV status in real time. First, on the top left, we monitor the battery. So the graph show battery temperature and also battery voltage varying with time. For safety, an alarm will trigger if the temperature goes above 50 Celsius or if the voltage drop below 250 volt. And then below that is the tire monitoring section. We use gauge to show the current reading, and next to them we combine both tire temperature and tire pressure into one single graph that varying with time. And then an alarm will trigger if the tire pressure goes above 33 psi or if the tire pressure exceeds 50 Celsius. And then at the bottom left, we also track the driving speed, which is also include a graph showing speed varying with time. So let's say if the driver exceeds 100 km per hour, the system will trigger an alarm. And then finally, on the right side, we have the alarm and warning panel. So this is where everything comes together. So if there are any dose limit I just mentioned cross, the activity warning icon in here will change color from green into red, and then the number next to it count the active warning in real time. So let's say, for example, if both of speed and battery temperature cross the limit at the same time, so this number will show 2. And then below the counter, the alarm list log all recent warning activity. This makes it very easy for the user to monitor exactly what went wrong and what when it happened. Moving on to predictive analysis, first we're going to see the time series analysis for battery temperature. So this graph shows the battery temperature over time. Normally it is stable between 25 and 35 Celsius, but sometimes it spikes past our 50 Celsius safety limit, and it is shown by the red line. In a way to prevent the battery damage, our system uses predictive analysis. If it detects a sudden jump like 10 Celsius in short time, it predicts an overheating event. So instead of reacting late, the system uses this prediction to turn on the cooling system before the temperature even hit 50 Celsius. Moving on to the next part, which is effect of driving speed on EV battery voltage. So this graph showed how driving speed affect battery voltage. Normally, the voltage is stable between 350 to 390 volt, as shown by the red line. But if we look at the green dot, the voltage suddenly drop at 200 to 250 volt, and this dangerous drop happen at both normal speed and high speed. A normal system only warns us after it drops, which can cause sudden power loss. So to prevent this, our system uses predictive analysis. By analyze this voltage drop at different speed, it predicts a battery or BMS failure early. This allowed the system to warn the driver before the permanent breakdown happened. And then the last part, we will talk about the effect of tire temperature with tire pressure on EV. So normally if tire pressure goes up, the pressure must goes up too. But as we can see, our basic predictive model failed to work here. Why? Because if we look at the bottom dot, the temperature increase but the pressure stay low. So the model cannot read this properly. But this abnormal data actually mean there is a slow tire leak. So to fix this failure, we need a smarter approach. So in the future, we will use rate of change algorithm, and then we train with the better data. Using ROC and clean data, the system will accurately predict slow leak or blowout before they become more dangerous.
Before we end our presentation, we have a few suggestions to improve this project in the future. First, we suggest creating a mobile app. Right now, the driver needs to look at the Thingsboard web dashboard to see the alarm. In the future, we can connect in the system to a mobile app, so the warning notification will be sent straight to the driver's phone. This is much faster and safer for the driver. Second, we recommend using edge computing. This means we can put a small device like a Raspberry Pi inside the car to process the data. This will make the system run faster and trigger the alarm instantly, even if the internet connection is slow. In conclusion, our demonstration proved that we have successfully achieved all three of our project objectives. First, we successfully developed an IoT system to track multiple EV parameters in real time. Second, we utilized Python and predictive data analysis to successfully detect abnormal thermal condition, as shown in our Jupyter notebook demo. For the third objective, we have tested and evaluated the system effectiveness. This proved the system is highly effective in solving the EV safety issue and preventing sudden mechanical breakdowns. And we have suggested two methods to improve our EV monitoring system. I think that's all from our group. Thank you very much to our lecturer for your time and attention. Assalamualaikum.